distance protection, while the hybrid is the zone 3 reverse blocking element. So your zone 1 and your zone 2 protection is looking forward, while your zone 3 protection is looking at the back. So if my fault is internal, which is from one line to the other line, I will trip immediately. But if the fault is at the back, I will not send a tripping signal on the other end. The first single line diagram, we have that we're using an oil field cable. The 230 kb cable is 2000 MCM copper, and we buy this directly from Oslo, Norway. I think the cost of the cables, like maybe there's 9 of them, is like $1 million US, just the cable alone, 1,500 feet, oil field cables. So the cable here, the 230 cable from the transformer goes up to the switchyard here. This is the 230 kV switchyard, and this is like 1,500 feet. Okay, so that cable, 1,500 feet, there's 9 of them, and it's costing us $1 million US to buy this all the way from Oslo, Norway. Okay. One of the very tricky design of the switchyard on the top of the mountain is that the snow goes high. So this is now the cable. This is the oil field cable all the way down to the generators, 1,500 feet. So you have the oil field cables here. You have the cable terminator, and this wire here goes to your switchyard, to your the bus, Okay, very very intricate cable termination. Okay. During winter time, the snow that we collect to become water is just so much, so wide, like 128,000 acre feet, probably like 60,000 hectares, something like that, of snow, such that this is the 230 kV SF6 gas circuit breaker. What is an SF6 gas circuit breaker? 230,000 volts SF6 gas circuit breaker. Any takers here? Go ahead. Very good. Now you've got a chocolate here. It's a sulfur hexafluoride. So the SF6 is very good. The SF6 gas circuit breaker becomes your, your cooling medium and interrupting cooling medium. So this circuit breaker here is elevated around 10 feet above the ground. So I have a circuit breaker, and we put a platform 10 feet above the ground because during winter time, all of these are all filled with snow. So we cannot operate the breaker if there's snow, right? So we have to raise the circuit breaker 10 feet above the ground. Can you imagine that? And going to the substation, 10,500 feet above sea level, we have to use snowmobile or catmobile to go there. This is a CCVT, and this CCVT is called. What is the name? What is the meaning of CCVT? Any takers? This is one of your instrument transformer that provides power to your relays and metering units that became usable for metering and protection. Any takers? CCVT. Not yet? Okay, so your CCVT is your coupling capacitor voltage transformer, right? Or your potential transformer. The circuit breaker, right? Okay. Yeah, the voltage is 230 kV, and normally the continuous current capacity is like 2,000 amps, for example. And the short circuit current capacity is 63,000 amperes. So it can interrupt current at 63,000 amps, while the continuous current capability is 2,000 amps. Steady state, you can open and close your breaker at 2,000 amps. So the CCVT is your potential transformer, and this potential transformer is the one feeding your meters and your protective relays. So we're using 67 volts line to neutral for the relays and 120 volts for the meters. Okay, so this CCVT, the ratio of this CCVT is 2000/1155 is to 1, So 230 kV divided by 2000 is how many volts? 230,000 volts divided by 230,000 divided by 200. 2,000 is how much? That's the voltage to your relays, which is around approximately 67 volts. Okay? So this is the 230 kV bus on the switchyard. This is your cable terminator here. This is your oil field cables. So this is the cable. What do you mean by MCM copper? 2,000 MCM copper. Any takers? Go ahead. MCM? Oh, you're speaking electronics, huh? Oh, we speak electric power here. MCM means? Go ahead. Huh? No, it's not mega. This is cable, go ahead. Are you microphone?
Metric circular mill. Metric.
Metric?
Yes.
No, not metric. Go ahead. Very good. 1,000 circular mills. Okay. M means 1,000 here. Congratulations. Doon ako sang chocolate out eh. Okay, next we were doing the final testing and commissioning of the relays. So what we have here is the set Bravo relays or set A relay, and this is a Schweitzer SEL 300G generator relays, and this one is the I think the GE relays here. Okay. Okay, we have some motor relays here. These are some of the other differential relays and transformer relays here. So we're doing the final testing during the time and if you are the systems protection engineer that does all the relay settings and calculations, you have to go out in the field, provide all the testing fault files for you to validate all your settings and calculations are correct and it operates properly. Okay, this is the single line diagram of the power plant. So we have the generator here. We have the motor operated disconnect switch. So during generation, it becomes an ABC phase sequence, and during motor operation, it becomes an ACB phase sequence, for example. So this is our generator step-up unit transformer, and we have here the auxiliary transformer on the side. If you have any question, please let us know, okay? This is now the single line meter relay diagram. It's not so clear, but I will share it with the other one. Okay, this is now the fun stuff. Hopefully, you guys will be learning a little bit about generator protection. Okay? So this is our generator, and this generator is being protected by your protective relays. This is the generator here. So we have this generator differential transformer 87G, and also we have this high side overcurrent here. The 27 device is your under voltage relay. This is the 78 device is for your 78 loss of synchronism. This is the 32 device is your reverse power for your anti-motoring. 49 device, your 49 device is your thermal protection, right? The 46 device is your negative sequence device. And the other one is your 21 device and your 51V. Your 21 device is your phase distance protection relay. Your 21 device is just your backup device to protect your generator from the outside system faults. So your system faults outside is being seen by your backup phase distance protection using zone 2 protection. And your zone 2 protection is normally set at around 120% of the apparent impedance of your next transmission line. So you have the generator impedance, plus you have also the transformer impedance, plus you have also the transformer impedance of your line. So 120% of that, if you add those three, will be your backup phase distance protection. And X1 plus X generator plus X the transformer plus X of the line will be your apparent transmission line impedance. Your generator has this hydroelectric power plant has a high impedance grounding protection. And this high impedance grounding protection utilizes the distribution transformer. And this distribution transformer normally rated like 75 kVA or 50 kVA. And the resistance here across this grounding of the generators. There's normally like 3 types of grounding in your generator. You have a high impedance grounding, a low impedance grounding, and also a hybrid grounding. High impedance grounding is the impedance across this, the impedance across here is very high, and the low impedance grounding is the impedance on this primary side here is very low. The hybrid is a combination of both. We utilizes the high impedance grounding for this generator because of the fact that we would like to limit the short circuit current during ground fault on the winding of the transformer around 10 amps to 25 amps, from 10 amps to 25 amps. So the resistance here is normally like 0.351 ohms, or what you call this 0.78 of an ohms, depending on the capacitance of your generator, plus your cable here, plus your transformer here. So you will treat this generator just like a transmission line impedance. You have a transmission line, and then you have a capacitor from your transmission line to the ground. That is your capacitance. Okay? Do we have a break here after 1 hour or what? Let me finish this portion here and then we'll take a small 15 minutes break, then come back, okay? So here we have this 59N device, and this is the resistor here. So the 59N device is your ground over voltage relay, and this ground over voltage relay is looking at your zero sequence voltage across this distribution transformer here. And this zero sequence voltage is normally the summation. If you're using a three-phase system, that's the summation of that. And if you're using a single phase one here, it's the elevated zero sequence voltage of the neutral of your transformer here. Okay, normally set like 5 volts or 6 volts or 9 volts, depending on the design of your system. We have the 59 device, which is your over voltage protection. 59 device, we set the over voltage protection like 120 to 130% of your voltage for your protection. The 27 device is your under voltage relay. We normally set those at 80% of your voltage, to your relay. This is a delta transformer and a Y transformer. Most of the protection for the transformer now is only set and designed inside the microprocessor relay. It can, if you have a delta transformer here and if you have a Y transformer here, normally when we design our current transformers going to the transformer differential, the Y side of this transformer here will be connected delta, and the delta side of the transformer will be connected Y. However, for brand new microprocessor relays, you can set the current transformer connection all Y grounded and Y grounded, and just change the phase displacement inside the relay 30 degrees out of phase, and you can do it easily inside the relay. So it's very easy for you to connect the current transformers Y grounded easily, and the relay will compensate for the phase angle difference inside between the two winding of your transformer. Before we go further, any question that I can answer? Or go ahead, Dr. Vencer. Okay. Correct. It's yeah. Correct. Yes, the States is still using the English system, and most here in Asia and probably in the Eastern countries, they're using metric system now. So I'm very familiar with the English system and the metric system. We were studying that in the National Electrical Code here with Engineer Armadillo during those times, So, very good point, Dr. Vencer. Other questions before we proceed forward? Very, very low voltage, it will be protected by your under voltage relay, which is your 27 device, and this is approximately, for example, at 80% of your nominal voltage. So 67 volts times 80% will be your setting. And this is normally set at around 3 to 5 seconds. 3 to 5 seconds. For the overvoltage protection, which is your 59 device, the overvoltage protection in the relay protects, the insulation of your cables and of your generator windings, for example, set at around 120% of your nominal voltage. The overvoltage protection at 120% is normally set at instantaneous tripping, like 2 cycles to 3 cycles of your time, which is 2 cycles is around 32 milliseconds, and 3 cycles is probably around 48 or 50 milliseconds.